Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 36th lecture. In this lecture, we will be continuing with the concepts which are important for physical design. Specifically, in this lecture, we will be looking at signal integrity, antenna effect and library exchange format or LEF files. So, in the previous lecture, we had looked into that the interconnect is lying and there are many interconnects in close vicinity of a given interconnect, and that gives rise to coupling capacitance, right. So, there is a coupling, there is a capacitances between interconnects, and there exists coupling capacitance, and because of coupling capacitance, what happens is that the voltage in one interconnect can impact the voltage in the other interconnect, meaning that if there are two interconnects lying in close vicinity, if there is a change in voltage in one of the interconnect, then there is some impact in the voltage in the other interconnect also. Ideally, there should not be any impact, but because they are sharing the dielectric and they are coupled electrostatically, therefore, the voltages of one interconnect impact the voltage of another interconnect, and this creates what is known as signal integrity issues. Now, signal integrity issues are of two types. The first is related to dynamic delay variations, meaning that the delay of the interconnect delay associated with one interconnect is impacted by what is happening in the neighboring interconnect, right. Ideally, that should not happen, right. So, the delay of one interconnect should not be dependent on what is happening in the other interconnects, but because of coupling and signal integrity issues, the delay of the associated with one interconnect becomes a function of what is happening in the other interconnect. And also sometimes the activity on the neighboring lines can create functional issues in our circuit. So, we will be discussing these two manifestations of signal integrity issues in subsequent slides. Now, to understand dynamic delay variations, let us first understand that what is the delay which is base delay, meaning that if we do not consider activities in the neighboring wire, what is the delay value that we expect, right. That is known as base delay. Now, to understand base delay, consider this circuit. There is one inverter driving another inverter through an interconnect, and there is another inverter driving another inverter which is through another interconnect. But these interconnects are lying in vicinity, and therefore, there is some coupling capacitance CC, and with the line A, right, with the line A, there is a ground capacitance also which we say CG, right. Now, whenever we are considering, whenever we want to study signal integrity issues, then the line where we are observing the effect of signal integrity, that we say that is the victim line, right. And the line which is causing the effect on the victim line, that is known as the aggressor line, right. So, let us assume that A is the victim, right, and B is the aggressor line, right. Now, if we assume that then let us assume that the gate G1 makes a 0 to 1 transition, meaning that initially the voltage of this point A was 0 volt and later on it rose to say VDD. Initially it was 0 and it rise to VDD. So, there is a 0 to 1 transition on the victim line. Now, the driver G1 provides a charge from the ground capacitor, charge for the ground capacitor CG to change from 0 to VDD. Now, this point was initially when the line victim line was 0, this point was 0, right. So, the voltage across this capacitor CG was 0 and this point is grounded. So, 0 minus 0 is 0 volt, right. So, initially it was 0 and later on when A line changed to VDD, then this point became VDD, right. Now, voltage across this capacitor becomes VDD because the other end is grounded, right. So, the capacitor CG got charged from 0 to VDD voltage, right. So, the capacitance CG gets charged because of the transition in the line A, right. When line A changes from 0 to VDD, the capacitor CG gets charged, right. Now, what about the capacitor CC, right. Now, capacitor CC, whether it will be charged or not, let us see, right. Now, the line B is having no activity, meaning that it is not changing, but it can be either held to constant 0 or constant 1. So, let us understand that what will be the behavior when the line B is held constant at 0. Suppose B was held constant at 0, right. So, initially this capacitor voltage was, initially the line A was 0 and B is held to 0. So, initially the capacitor CC was 0 and what is the value of the voltage across this capacitance, right, between VA and VB, right. So, so we can say the voltage across this capacitor CC is VA minus VB, right. Initially it was 0 and finally VA points changed to VDD while VB remained constant to 0. So, the VA minus VB is equal to VDD, right. So, G1 needs to provide a charge for coupling capacitance CC to change from 0 to VDD. So, the capacitance the voltage across CC was initially 0, right, whenever when the victim line was 0, the voltage across the capacitor CC was initially 0 and later on it became VDD, right. So, it means that CC is being also charged in addition to CG, right. So, when B is held constant to 0, then G1, that is this driver needs to provide the charge, and how much charge it will be providing? It will be providing charge sufficient to charge the capacitor CG plus CC, right. Next, let us consider that B is held constant to a value of 1, right. So, let us see that B is held to constant 1 or VDD. So, this VB is VDD, right, and A is changing from 0 volt to VDD, right. So, what is VAB initially? VAB initially is 0 minus VDD is equal to minus VDD, right. And what is VB finally? VB final is VAB final, that is voltage across the capacitor CC after A has transitioned to VDD. So, in that case the VAB, that is voltage across the capacitor, is equal to VDD, VA is VDD minus VB, VB is also VDD. So, VAB is equal to 0. So, what is the change in voltage across the capacitor? It is 0, final value is 0 and initial value is minus VDD. So, 0 minus VDD, right, and that comes out to be plus VDD, right. So, what happens is that the capacitor CC also needs to be charged by the voltage VDD, right. So, what it means is that if the line B is held to constant 1, then also G1 needs to provide a charge to charge the capacitor CG and also the capacitor CC, right. So, it means that the delay computed by assuming aggressors are held constant logic is known as base delay, and it is the same for the case when the other line is at 0 or 1, right. So, the base delay is same whether the aggressor is 0 or 1, right. So, whenever we do delay computation, for example, when you are doing static timing analysis, internally it will do delay computation. Now, during delay computation, what will the delay calculator do? So, if we do not consider signal integrity effect, then the delay calculator will compute what is known as base delay, and the base delay will correspond to charging of capacitor Cg plus Cc, right. So, this will be what the delay calculator will do. Now, let us understand that what will happen if the line or the aggressor line was also changing, right. So, assume that G1 is G1, that is driver of victim line A, makes a 0 to 1 transition, same as earlier, right. It is making 0 to VDD transition, and let us assume that B also makes a 0 to 1 transition, 0 to VDD transition, the B lines, right. So, in this case, what is the initial VAB, voltage across the coupling capacitor? VAB is equal to 0 minus 0 is equal to 0. And what is the final voltage across the capacitor? Again it is VAB is equal to VDD minus VDD, right. Again it is 0. So, the coupling capacitor is the initial voltage is also 0 and final voltage is also 0, meaning that the coupling capacitor is not being charged. Hence, less charge needs to be provided by G1 for charging Cc compared to the base delay. In the base delay, Cg plus Cc was being charged, but when both are transitioning in the same direction, then Cc need not be charged because that voltage is not changing, right. And therefore, driver of G1 or the driver G1 must need to supply only less charge, right, and therefore delay of G1 will decrease. So, if we look into the do exact simulation, we will get waveform something like this. So, if this line G1 was the victim line A, initially it was transitioning like this, right. After we incorporate the SI effect, it will show a transition something like this, and if we say take for 50% mark as delay, right, that will shift towards left in the time domain, and we can understand that the delay has actually decreased, right. So, this effect is modeled as negative incremental delay over the base delay, right. So, this is the base delay, right, this point corresponds to base delay, and this point corresponds to the delay that will get if both the victim and aggressor are transitioning in the same direction. Now, let us take the situation when G1 is again transitioning from 0 to VDD, right, but the line B is transitioning in opposite direction, meaning that it is transitioning from VDD to 0 simultaneously, right. These two transitions are happening simultaneously. So, in this case, what was the initial charge across Cc? It is VA minus VB is equal to 0 minus VDD, right, that is minus VDD, right. And what is the final VAB? That is VA minus VB, that is the charge, sorry, the voltage across the coupling capacitor Cc, it is VDD minus 0 is equal to VDD. So, what is the change in voltage across Cc? It is change is VDD minus VDD, right. So, it is 2 times VDD, right. So, what is happening? The polarity of the voltage for this capacitor Cc is changing, therefore, 2 times the voltage change we are seeing, right. So, voltage across Cc is minus VDD initially and plus VDD finally, hence in effect 2 Cc needs to be charged by G1. So, if we consider charge is voltage time Q is equal to CV, right. So, voltage times capacitance. So, if we are considering charge, in a sense we can think that instead of making 2 times voltage change, we can think that it is charging twice the capacitor, right. So, we can think of it as 2 TC, 2 Cc is being charged, right. So, now in the base delay case, Cg plus Cc was charged, right. Now, in this case, when the transition is happening in opposite direction, Cg plus 2 Cc is charged, right. So, more charge needs to be supplied by G1, and therefore, we expect that the delay will increase, and if we do the simulation, then we will see that in the time domain the curve will shift towards right and the 50% point will appear later, right, and therefore, the delay will increase in this case. So, this effect is modeled as positive incremental delay over base delay, right. So, what happens is that the tool uses, so when we do static timing analysis, by default the tools assume that there is no activity in the neighboring lines, and they compute delays based on base delay and they report the numbers based on it, right. But there are some tools which do analysis based on or take into account signal integrity issues also, right. In those tools, the base delay is adjusted by positive or negative incremental delay, so that the effect of signal integrity is accounted, and therefore, the slacks, the setup slack and the hold slack, those numbers will change after we are doing signal taking into account signal integrity effects. Now, let us look into what is a noise or glitch, how that gets introduced because of activity in the neighboring lines. So, a glitch can occur in a victim line, victim net held at a constant logic value due to transition in the aggressor net. So, glitches are also known as crosstalk noises. Now, depending on the value of the victim net and the type of transition of the at the aggressor net, 4 types of glitches are possible, right. So, what are the 4 types of glitches? So, the logic 0 has a rise glitch. Suppose there was a signal which was a line, a victim net which was held at constant 0, logic 0. Then there can be a rise glitch, like it can be the 0 volt, there will be some voltage, right. Above 0 volt it can go, or it can show an undershoot also, it goes into the negative direction, right. So, and also if the victim line was held at constant 1, then it can come down because of the glitch, right, for some time duration, right. So, this is known as fall glitch, or it can overshoot, it can go even above VDD, right. Sometime it can go because of feedback and other elements in the transistor, right. So, because of Miller effect and other coupling between input and output nodes, sometimes the voltage can go above VDD, that is overshoot, and sometimes it can go below ground also, those are undershoot. Now, how are glitches created? So, again let us consider a circuit, right. In this case, we are not showing the ground capacitance just for simplicity. Now, let us assume that A is the victim line, this is the victim line, and assume that A is held at a steady state at logic 1, right. So, this VA is basically initially VDD, right. Now, assume that line B is also held steady at VDD, right. Now, voltage across this coupling capacitor is VAB, VA minus VB is equal to VDD minus VDD is equal to 0 volt, right. Now, assume that the neighboring line makes a quick transition from VDD to 0, right. Now, this is making a transition from VDD to 0, right. So, in this case, the coupling capacitor now gets charged to, now what will be the VAB, right. VA minus VB will be VDD minus 0 volt, right. So, after the transition the VB line becomes 0. So, we have VDD, right. So, the coupling capacitor now gets charged to VDD due to voltage difference in the lines A and B, right, and the driver of the line A, driver of this line A. So, this there is a driver, right. So, this is connected to VDD, right. So, internally this inverter will have a PMOS, right, and an NMOS, and this line is at VDD, right, and this is line A, right, and this is the point VDD. Right. Now, this this line is A, right. Now, this line, this coupling capacitor Cc needs to be charged. So, to charge that, some current will be drawn from the VDD, right, from VDD through this PMOS to the line A, and then the charge Cc will be, or the coupling capacitor Cc will be charged, right. Now, whenever the current is drawn, now this PMOS is switched on, but still it will have some resistance, right. It will have some resistance, and because of that resistance there will be, and the current flowing. So, you can consider that there is a resistance R and the current is flowing, right. So, there will be an IR drop, right, and because of that drop there will be a drop in the voltage in the line A, right. So, the driver of line A will supply this charge and it will cause a temporary dip in the voltage of the line A, because the PMOS that is showing some resistance, there will be some voltage drop through it when it is supplying current from the, or drawing current from the power line, right. So, the waveform that we expect will be something like this. So, the A line is held constant, but whenever the B line is falling, B line is making this transition, there can be a dip in the voltage of A line. Ideally, there should not be any change, right, neighboring lines should not impact, but because of the existence of this coupling capacitor, the voltage can drop below VDD in the line A. Similarly, when the aggressor line B makes a 0 to VDD transition, then there can be bump in the voltage of the victim line that was held at constant logic 0, right. So, similarly, it can happen in the, when the A line was at 0 also, because of the current being drawn from the driver, there will be a change in the voltage, right. Now, on what factors the magnitude of these glitches will depend? So, this glitches magnitude will depend on how quickly the transition happens in the line B. If it happens very quickly, then if this line was transitioning very quickly, suppose there is one transition, another transition is like this. So, in this case, when the transition is happening very quickly, then the glitches can be more. So, glitch increases when the aggressor line transitions quickly. Then the coupling capacitance between the aggressor and the victim line, right. If this capacitance increases, if the glitch increases with the increase in the coupling capacitance, if this capacitance increases, right. Now, if the ground capacitance of the victim net is increased, right, then the glitch will decrease. So, glitch decreases as the ground capacitance of the victim line increases. Suppose there was a ground capacitance, right. So, what will happen is that whenever this one is transitioning, some charge will be supplied from this capacitor also, and therefore, the charge needed from the victim driver, that will be less, and therefore, the drop will be lesser. Now, it also depends on the strength of the driver, right. If the strength of the driver is increased, right, then what happens is that the resistance of the PMOS, that will be lesser, and therefore, the IR drop through that driver or the PMOS transistor will be smaller, and therefore, the glitch will decrease. So, glitch decreases as the strength of the driver of the victim net increases. Okay. Now, when will this glitch cause functional problems? So, glitch, if the magnitude of glitch is above a threshold, it can propagate to sequential circuit element. Now, there is one line, right, and because of the activity in the neighboring line, a glitch was created. Finally, it will go to say an inverter and then through something logic, and finally, it can reach a sequential circuit element D, right. Now, if the magnitude of this glitch is above a threshold, then it can propagate to sequential circuit element and consequently a wrong value can be latched, right. So, suppose there was a glitch which was of a large magnitude, this the D was expected to be VDD, right, and it dipped so low that instead of 1 a 0 was latched by this flip flop, right, and then it can lead to a circuit failure because a wrong state is being captured by this D flip flop, right. So, the height of the glitch if it is above some threshold, and also the width is also important, that if there is a very narrow glitch of short duration, then usually it does not cause problem in the circuit. But if the magnitude of glitch is above threshold, on the clock and reset or control signals, a spurious transition can get triggered in a sequential element, right. If the glitches are on the clock path and the reset part, then those can be detrimental to our circuit, and we should be especially careful about the glitches in those parts of our circuit. And tools need to propagate the glitch, right. So, there are models in the technology libraries we have not looked in earlier lectures, but just for take a note that the technology libraries also contains noise models, and using those noise models, tools can compute the effect of the noise in the gate, and then it can propagate it throughout our circuit, and using that propagation we can understand that whether there are chances of wrong state being captured by our in our circuit, and whether the glitch can cause circuit failure, right. So, once we do physical design, at the end we also do sign off. So, during sign off, this taking into account signal integrity issues and noise issues are very important, right. So, we will be looking into this in some more detail when we discuss sign off. Now, there is another concept of or another phenomenon which is known as antenna effect, which we must consider during physical design. So, what is antenna effect? So, consider this layout, right. So, in this layout we have there is a driver, right, there is an say inverter, right, which is driving. So, the inverters PMOS and NMOS at the output, those are the drain region. So, this is the driver's drain region, right, and then it is connected to another inverter through an interconnect, right. So, this is another inverter which is connected. So, in the input of this is a gate, right. So, this is what it is showing. So, this is the gate oxide, this is the gate oxide, and we want to connect this inverter which is the driver and the another one, right. So, we are just in this figure we are not showing all the, so the ideally this should be like this, right. The first inverter G1 and this is G2, right. This is VDD, this is VDD, this is PMOS and this is NMOS, right. So, this is the interconnect we are talking about, right, and this is the basically the drain, right, which is shown here. For the other we are not showing, for simplicity we are showing only one drain and only one. Now, these are the gates, right, these gates of these two transistors. Now, for simplicity we are showing only one gate, right, and this is connected through metal layers, right. Now, note that in this case what is there, the metal line 1 is connected to this gate, and here also metal line is there, and then there is it is going through a VR to metal line 2 and then coming down again through metal 1, right. So, now what happens is that during fabrication we fabricate layer by layer. So, first we will be fabricating metal 1. So, during the fabrication of metal 1, so in the fabrication process many a times we use plasma etching, ion implantation and such techniques, and by exposing these metal lines to plasma. So, plasma contains charged ions, electrons and positive and negative ions and also neutral atoms, right. So, from this plasma what happens is that such charge can get accumulated on the metal lines, right. Now, note that in this case the second metal lines is not yet created, right? Only the first metal line is created. Now, if this charge gets accumulated in this metal line 1, right, then this metal line 1 is connected directly to the gate, then the whatever the charge is there, it can get discharged through the gate, right. And remember from the last lecture, gate is a very thin material, right, a few nanometers, 2 nanometers, 3 nanometers in that, and contains only a few atoms and tens of atoms, right. So, if that is the case, then if a charge is sufficient and a high amount of of charge gets discharged or crosses this gate oxide, then gate oxide can get damaged, right. And this is known as basically antenna effect, and the other name for this is plasma induced gate damage, right. So, this can happen during fabrication, right, but why did it happen? Because the layout was made such that the metal one was directly connected to the gate, and there was no other path for the charge to flow, right, and therefore, this is not a good structure. We will see how to modify this structure, so that antenna effect or the gate induced plasma induced gate damage can be restricted. So, to understand that what is the probability of getting damage, we define a quantity which is antenna ratio. It is the ratio of the conductor area to the gate oxide area. So, conductor area, A conductor divided by A oxide, right. So, the antenna ratio basically defines that if the say A conductor area is larger, then the charge accumulated will be large, right, and therefore, the chances of damage is larger. Now, if A oxide is large, then the same charge is distributed over a larger area, right, and therefore, it is we expect that if A oxide is large, then antenna ratio will be smaller, right. So, high antenna ratio implies greater chance of damage, and antenna rules define. So, in libraries we have the antenna rules which define that what antenna ratio is permitted. Above that, there is a violation. If we find that violation, then during physical design, we need to fix those DRC violation or antenna DRC violation and make it smaller. How we can do? We will see in the subsequent lectures. Now, let us look into another important aspect of physical design, that is library exchange format files, right. So, from our last two lectures or discussions from last discussions that we had in last two lectures, we can understand that the fabrication process has a strong effect on the physical design task. Therefore, we need to capture the information of fabrication during physical design, right, somehow, and we capture that information using a file which is known as library exchange format file or LEF file, right. Now, LEF file is generally divided into two parts. The first part is known as technology LEF file, and the second part is known as cell library LEF files. Now, what does technology LEF file contain? So, technology LEF file contains information about the available layers, vias and their properties. It also describes the sheet resistance and the capacitance per unit square for various layers, and it also contains some placement and routing design rules and also the antenna rules that we just discussed. And the cell library LEF files contains information of the cell, right. So, during physical design, we need to place the cells and route it, right. So, we need some information of the cell about the physical attributes, right. What is the bounding box, where the pins are and so on. We don't know, we don't need the exact layout of the cells that we are going to use in our layout, but some abstract information. And that abstract information of the layout of the cell is there in the cell library LEF files. So, it contains abstract information of the cell layout relevant to the physical design and the cell boundary, list of pins and their locations and obstructions to placement and routing, right. So, these are important for creating the placement and routing of our design on the layout, right. So, when we do physical design, then we need to give this left files. There are other ways also to give this information, but giving the information through the left files is one of the most popular method. Now, if you want to know more about these things, you can refer to these books. And just to summarize, so in this lecture, what we have looked at we have discussed signal integrity issues, and we looked into antenna effect, and we also looked into the left files, right. So, with this lecture, we have completed the basic concepts that are important or essential for appreciating the physical design task. So, from next lecture onward, we will be looking into the each individual physical design task in more detail. So, we will start first with chip planning. So, that is it for the lecture. Thank you very much.